Welcome to Train Signal. You're watching a lesson on IP addressing. So as we move along through a series of lessons here on networking, one of the key things to understand when it comes to networking is what an IP address is. Right? We need to know what it is, what it's used for, and how we basically communicate from one computer to another using these addresses. So what is an IP address? Well, it is a 32-bit address, and before I go any further than that, let's talk about 32-bit. If we go back, we've talked about bits in other lessons. A bit is a 0 or a 1. Okay, so if you picture a string of 32 zeros and ones put together, that's what makes up an IP address. But this string of 32 ones and zeros is used to uniquely identify a computer on a network. Okay, so when you're thinking about how you have a computer that you're sitting at and somebody else in the office has a computer that they're sitting at, the way you are able to successfully transmit information from your computer to their computer, and for the computers to know, oh, okay, that's the computer I'm supposed to send stuff to, and for that computer to say, oh, that's the computer I'm getting it from, they have to have some kind of identifier, and that identifier is an IP address. Now, what we know about these IP addresses is that they're actually made up of two significant, I was going to say components, but we'll say sections, okay, or portions. And one portion of the IP address is what's called the network ID, and the other portion is called the host ID. And what we know is that it's the left side of the IP address that makes up the network ID, and the right side that makes up the host ID. Now we're going to take a close look at this in just a moment, because we know it's the left and the right, but we don't necessarily know where the breakdown is between the network ID and the host ID when just looking at an IP address. But before we go there, let's talk about what network ID and host ID means. The network ID represents the network that the computer resides on. Okay, so even within an organization, you might have different networks. In some cases, you might hear it referred to as different subnets within a network. Okay, so the network ID represents, it's an identifier for what network the computer is on, and the host ID will uniquely identify the computer on its particular network. Okay, so once I know what network I'm on, I get a unique identifier within that network. The way I like to think about it is kind of like a street address. Okay, in other words, you might live at 123 Main Street. Well, Main Street is the network ID. It's what street you live on. And then within that street, 123 represents the specific house, right? Because, the next street over might also have a 123, and there's a lot of different houses that might have the actual number 123. Okay, that 123 is the host ID. Okay, so that's how I like to think of it. Is each computer resides on some street, and we'll call that street a network, and then it has a house number, and that's the host ID. So here we have an example. I have an IP address of 192.168.10.1. And like I said, I know that the network is on the left and the host is on the right. The problem is, where do I draw the line? How much of this series of numbers represents the network that I'm on, and how many of these numbers represent the host that I am? The way we would determine that is with something called the subnet mask. Okay, so with every IP address, whenever you see one, it should also come with a subnet mask. And the subnet mask, for simplicity's sake, okay, we're not going to get too advanced with this, because if you really want to get deep into this, you can watch the Network Plus course, okay, and that's something you may want to do after A+. In Network Plus, we'll break down how the subnet mask isn't always 255s and isn't always zeros, because we look at things from a binary standpoint, right, with the bits and the ones and zeros. But for now, for simplicity, when dealing with these decimal numbers, and saying that we are going to divide the network ID and the host ID based upon where one of the dots are in an IP address, if we had a subnet mask of 255.255.255.0, that means that the first three numbers, and by the way, those numbers are called octets. The reason they're called octets is because of the 32 bits that make up an IP address, we break them down into 4 sets of 8. And each of those 8-bit sections are called an octet, right? Oct for 8. Okay, so that's where the 192 comes from, is because that's actually 8 bits make up the 192. 8 more bits make up the 168. 8 more bits make up the 10, and then 8 more bits make up the 1. In this case, wherever there's a 255, it's the network ID, and wherever there's a 0, that's the host ID. So if this is what we had, that means that the network ID for this IP address is the 192.168.10 network, and the host ID for this particular computer on that network is simply 1. But if we change the subnet mask to 255.255.0.0, but keep the same IP address, we change things a bit. Now we have a network represented as just being the 192.168 network. And the unique host ID on that network is 10.1. We could even take it a step further, and we have subnet masks that are simply 255.0.0.0, meaning it's the 192 network, and the unique identifier on that network is 168.10.1. Now, when you're figuring this all out and putting this all together, one thing to keep in mind is that obviously in the scenario here where we have a subnet mask of 255.255.255.0, well, there's a lot of various network IDs available, but a very small amount of host IDs available because we're only using one number for the host ID. Whereas when we jump all the way down here to 255.0.0.0, there's not a lot of variety in the different networks that we can have, but we have a ton of hosts that we can have on each network. Okay, so that's something that you keep into consideration. So now that we understand the general makeup of an IP address, right? We have the 32 bits, they're broken into 4 octets, and then represented as an actual decimal number that us humans like to look at, right? Because we don't like to look at ones and zeros, right? So the decimal numbers are easier for us to remember. I have an illustration here for you of just a very simple, basic network, right? And the idea here is that we have, well, there's a little device there in the middle of the picture, which we'll say it could be a hub or a switch. Again, we'll talk about those devices in another lesson. But we have a client computer and a server computer, right? Because clients and servers, they need to talk to each other on a network. And I've even thrown in a firewall, then connecting us out to the internet. Matter of fact, not only is it a firewall, but it's also a router, more specifically. And for the sake of this picture, it's a router. I want you to understand the idea of what a router is, because it's significant to understanding on how to configure an IP address. So the client computer has an IP address of 192.168.10.101 with a subnet mask of 255.255.255.0. What that means is that it is on a network which is called 192.168.10, right? That's the name of the network that it sits on, and it's got a unique ID of 101. Now I'm going to ask you to ignore the third set of numbers listed there for just a moment, because I want you to look at the server's information, which has an IP address of 192.168.10.201 with the same subnet mask of 255.255.255.0, meaning it's also on the network 192.168.10, right? So the client and server, they're on the same network. That means that their host ID must be unique. The client had a host ID of 101. The server has a host ID of 201. Now again, I'm going to ask you to ignore the third set of numbers there, so we can jump over to the router, which has an IP address of 192.168.10.200 with a subnet mask of 255.255.255.0, which means it's on the same network, 192.168.10, and it also has a unique host ID on that network of 200. In that scenario right there, these 3 network devices can all talk to each other because they're all physically wired in on the same network. They're all logically on the same network in the sense that they all have the same network ID, and they all have a unique identifier on that network. But here's the thing. The router serves a specific purpose. The idea of a router is to connect computers from one network to computers on another network. And so in this case, it's showing that it's connected to the internet, which is a massive network. Now, technically, if I filled out this diagram accurately and completely, the router actually would have a second set of IP addresses as well. Okay, in other words, there's two wires coming into the router. There would need to be two interfaces, and each one would have its own IP address. So there would also be an IP address out on the internet side. But I'm not worried about that for the sake of what I'm trying to teach you right now. What I want to show you right now, the purpose behind this network, is that both the client and the server also have a third set of numbers tied in with their configuration. It says DG. DG stands for Default Gateway. The default gateway, when configuring your IP address, represents where the computer should send any information that is going to go outside of its own network. Meaning, if I'm a computer and I'm going to go ahead and send something to somebody who's not on the 192.168.10 network, I don't know how to get it there. I can only talk to other computers that are on my network. So I need to send it to a router. And that router is the default gateway. So notice that both the client and the server have 192.168.10.200 configured as their default gateway. Oh, and that happens to be the IP address of the router in this illustration. And the router would then take that information and route it out to the internet. And again, that's a whole different conversation, a whole different lesson on how routers function. So now that we understand what an IP address is and how it is configured, right? And we're going to look at that again in a little bit here on how it's configured on a computer where you have your IP address and subnet mask, but then also a default gateway to get out of your network. There are some rules, and I've already gone through some of these with you in the sense that, like right at the beginning here, each of the four numbers in an IP address is actually called an octet because it represents 8 of the 32 bits. Okay, so the 192.168.10.101, there's 4 numbers and each one is an octet. Each bit, as we talked about, is a 1 or a 0. And because it's an octet, which means you're going to have anything from 8 zeros as the smallest number all the way up to 8 ones, which is the largest number, it means that each octet can only have a number from 0 to 255. You will never see a number smaller than 0 or larger than 255 in an IP address. One other little tidbit rule here is that the first octet cannot be 127. Okay, you're just going to have to remember that. Okay, you cannot start an IP address with 127. That entire range of IP addresses has been reserved for diagnostics. And it's interesting because out of that entire range, which is almost 17 million IP addresses, the only one that's really commonly used is something called 127.0.0.1. And you may even see that, by the way. You might even see a computer that's programmed with an IP address, where you're pointing to that for some reason. And it's what's known as the loopback address, or also sometimes known as localhost. In other words, if you were to send a packet of information to the IP address 127.0.0.1, that is a pre-programmed number that says, send it right back to yourself. Okay, that's your own local host. That's you. That's yourself. Some additional rules. The host ID, okay, so the rightmost portion of the IP address, cannot be all zeros, and it can't be all 255s. Technically, that should say all ones if we look at it from a binary aspect, but again, save that for the networking course. The reason it cannot be all zeros or all 255s is that if you have all zeros, that is a representation of the network itself. Okay, so when I say you're on the 192.168.10 network, the network ID representing that network is actually 192.168.10.0. You can't have all 255s because that is reserved as what's known as a broadcast. If you want to transmit something out on your network and it's meant for all computers on the network, not a specific one, then you would send it, and the example I have here would be if 192.168.10.0 is the network that you're on, 192.168.10.255 is going to be a broadcast for that entire network. Now, I mentioned to you about the subnet mask and about how you can have either 1 255 or 2 255s or 3 255s. And that actually has to do with something called class full IP addressing. Back in the day when IP version 4 was first created, and that's what we've been talking about here, by the way, throughout this entire thing is IP version 4. IP addresses were divided into different class ranges. We had our A class range, which is when you had a single 255, meaning the first octet was the network ID and the last three represented the host ID. So a very few number of networks fell into the A range, and a lot of hosts could be in those networks. We had a B class range, which is 255.255.0.0, and a C class range with 3 255s and 1 0. Now this has a lot to do with how addresses were handed out for actual internet use. And we'll talk about internet versus private IP addresses in just a moment. But the one other classification that we had that went along with this is you couldn't use the entire range of IP addresses that were available. The only A class ranges, not only did the first number represent the network ID and the last three represented the host ID, but you could only have numbers 1 through 126 as the first octet when looking at A class IP addresses. Okay, so guess what? There were only 126 of them. And guess who got them? The biggest of the big. And we're not even talking about major corporations. We're not even necessarily talking about a Microsoft or an IBM. We're talking about ISPs, Internet Service Providers, AOL, okay, back in the day, CompuServe, okay. They had these A-class ranges because guess how many actual IP addresses existed within that network? When you take the last three octets, if you multiply it out, you end up with 16,777,214 possible clients on your network. There's no company in the world that actually needs almost 17 million unique IP addresses, except the internet service providers, the ones who are giving you the IP addresses to get onto the internet. The B-class addresses, you knew them based upon the first octet. It would start with 128 anywhere through 191. And by the way, you notice there's a number missing between A class and B class? Yeah, it's 127. Remember I just told you a moment ago, you can't have an IP address starting with 127. That's been reserved. Your C class range are IP addresses that start with 192 to 223. And then beyond that, we did have a D class and an E class. D class, and I shouldn't say had, we still do have D class range. And those have to do with something called a multicast, where you can transmit once and there can be multiple subscribers who will receive the transmission. And then we had our E class for experimental. But primarily, let's focus on A, B, and C. Okay, you need to know the subnet mask. You need to know what the first octet range is to be in the A, B, or C class. This is if you're going to fall into the official classful IP addressing. Now again, it's a whole separate lesson and a whole separate course where we go in and talk about how we can break these rules. But for A+, this is the stuff you need to know. By the way, here are those actual numbers that I was just mentioning. I mentioned with the A class, there's only 126 of them, but you had 16,777,214 hosts in each one. B class, you have a little over 16,000 of them. You get a little over 65,000 hosts in each. In the C class, we had over 2 million of those. But if you had one of those, if someone actually gave you one of those, if an ISP said, here you go, here's a C class range, you only got 254 hosts. And if you add it all up, you end up with a little under 4 billion host addresses available. Does it sound like enough for everybody? Well, it did, but not anymore. And we're going to address that in just a moment. Before we do, let's talk about private versus public. Private IP ranges are a certain designated set of IP ranges within, those A, B, and C classes we were just talking about that are not valid on the internet. Okay? You won't be able to travel on the internet with these IP addresses. The A class range that's been reserved from internet use is the 10 network. Anything from 10.0.0.0, which of course that's actually the network, so we'll say 10.0.0.1, through 10.255.255.255, which is the broadcast, so we could say 10.255.255.254. Basically, if you have an IP address and it starts with 10, it's not valid on the internet. You can only use it internally within your own network. The B class range, or ranges, were anything that started with 172.16, 172.17, 172.18, all the way through to 172.31. If you have an IP address that starts with 172.16 through 31, it's not valid on the internet. And then we have the 192.168.anything. Now that's actually a C class range. It's 192.168.0, 192.168.1, 192.168.2, all the way through to 192.168.255. Those are actually the network IDs, not valid on the internet. Now you might be thinking to yourself, whoa, wait a minute. I know that I happen to be on a computer that has the IP address of 192.168, but I'm on the internet. I mean, heck, I'll tell you what, the computer I'm talking to you on right now has that IP address, and I do have internet connectivity. Well, the way that happens, and I have that posted for you here, is that any host that has a private IP address, you still can get on the internet with something called Network Address Translation, or NAT. Beyond that, I'm going to tell you, again, go watch Network Plus. That's outside the scope of this course. I'm not going to go into all the detail. But there is a technology that allows those private IPs to get out on the internet. Now, there is one other range of private IPs. I separated it from the first three because it has a different purpose. And it's a B-class range of 169.254. These are reserved for something called a PIPA, APIPA, Automatic Private IP Addressing. We're going to talk about a PIPA in just a moment. But that's a special type of IP addressing scheme, and, well, that's the IP addresses they use. But if you have any of those IP addresses, you can't natively browse the web. Although, most of today's companies use these private IP addresses on their private networks because A, it makes it more secure because someone on the internet can't directly communicate with an internal computer. They have to go through network address translation. And B, it helps us with the issue of running out of IP addresses. Remember the nearly 4 billion IP addresses? And I said, is that enough? And I said, we thought so at first, but we're realizing not so much. All right, well, one of the ways that we solved that problem is through network address translation and having all of our internal networks use these private IP addresses, and each company only needs one IP address to get out onto the internet. Do we have 4 billion companies? Probably not, but we still have issues. We'll address those. Now, when it comes to obtaining an IP address, we have 3 different ways that a computer can get its IP address. Statically, where you statically just type in the IP address in the configuration for that computer. You can get your IP address from a DHCP server. DHCP stands for Dynamic Host Configuration Protocol. It's a special server whose whole purpose in life is to host a database of IP addresses and hand them out as clients need them. And then the third way is through a PIPA that I mentioned a moment ago, where you dynamically give yourself a random IP address in the 169.254 range. Now, I have a couple of quick screenshots for you here. This is what it looks like in Windows when you are statically configuring an IP address. Okay, you see that the IP address has been typed in, 192.168.10. In this case, 243, with a subnet mask of 255.255.255.0 and a default gateway of 192.168.10.1. You'll notice in the bottom half there is also this thing called use the following DNS server address. And I'm also pointing to 192.168.10.1. I'm not going to go into a whole long lesson on what DNS is, but here's the short version. DNS does name resolution. It does other things as well. But as far as we're concerned here, it does name resolution. See, because we talked about how computers communicate with these IP addresses. But, you know, us humans, I tend to refer to us as being stupid humans. Now, don't be offended by that. I'm in that same pool with you. It means our brains, we don't like to remember another system by its IP address. We want to remember its name. That's John's computer. That's Ed's computer. That's Mary's computer. Or how about on the internet? I want to remember Microsoft.com, Google.com. Okay, I want to remember names, not IP addresses. DNS is a server which keeps a database of names and IP addresses and how they map together. So that when you go to your computer and you open up your browser and you say, I want to go to Google.com, the DNS server is what will convert that to an IP address and allow communication to take place. So that's what the DNS server entry is here. Now, this is if we were doing it statically. If we were to click the button that says obtain an IP address automatically and or obtain DNS server address automatically, you'll notice that the fields gray out, and the reason why is because there's going to be communication with a DHCP server, or at least attempted communication with a DHCP server to say, hey, I need an IP address. And then hopefully there's a DHCP server that has that pool and it hands you an IP address. But notice that when we are on this particular selection, there's another tab that wasn't there a minute ago. Let me go back. Okay, when doing statically, you have the general tab. When doing it dynamically, you have an alternate configuration tab that shows up. And it's in that alternate configuration tab, if we go there, that we can say, in the event that there is no DHCP server to service my needs, how am I going to get an IP address then? Through APIPA, automatic private IP addressing, where I randomly give myself a 169.254 address. It means I will not communicate with the internet, not even through NAT. I will not communicate through the internet. Matter of fact, I won't even have a default gateway. I will only be able to communicate with other computers on my network who are also using a PIPA. Can you tell that a PIPA is not really used? The other alternate configuration you could do is user configured, and this is where you would statically have a backup IP address. So you could theoretically go to every single computer, tell them all to dynamically get their IP address from a DHCP server, but then give them all unique alternate configuration in the event the DHCP server goes down. I don't see it done. We keep our DHCP servers up and running is what we do. That's how this stuff actually works. All right, to wrap things up with this lesson, the last thing I want to talk to you about is a real high-level overview of this thing called IPv6, because everything up to this point I've been talking to you about is IPv4. But there are some problems with IPv4. First of all, there's not enough addresses. Mentioned that we thought 4 billion was enough. It's not. We have very cluttered internet routing tables. Can't take the time to go into the detail as to why that is, but I'm telling you, that's a problem with IPv4. Very cluttered internet routing tables. Believe it or not, IPv4 can be very difficult to configure, even though I just mentioned we can do this thing called DHCP, which makes it quite simple. Relative to how things could be, it's considered difficult. And security is optional. We don't have to have security with IPv4. So that's why we have IPv6. First of all, we have plenty of addresses. The actual number of addresses is a number larger than I can actually speak. It's 3.4 times 10 to the 38th power. I don't know that anybody knows what that number would actually be called. It is a number that is so far out there, we will never run out of addresses. We also have simplified internet routing tables that go with IPv6. We have a much easier and more automated configuration with IPv6. Matter of fact, we don't even need DHCP. We can use all auto configuration and things work. And security is required, so we have much more secure communications when using IPv6. Just to kind of take a very quick look at what IPv6 addresses look like. First of all, they are 128 bits long, not 32. So you'll notice it's a very long string of ones and zeros. We couldn't possibly look at the number that way, so we look at it in 16-bit hexadecimal blocks. So basically we take 8 blocks. So instead of the regular IPv4 where we have 4 blocks of 8 bits, now we have 8 blocks of 16 bits. And we don't look at them with decimal numbers, we look at them with hexadecimal numbers. So the FE80 colon, we have a colon now instead of a dot in between each of these blocks. 0000 colon 0000 colon 0000 colon 05EE colon 00FF colon 0238 colon 47B1. Whew! That's a mouthful, isn't it? So why don't we simplify this a little bit by suppressing the leading zeros, right? We don't need to say 0000. We can just say that's 0. That block is just 0. So now we have FE80 colon 0 colon 0 colon 0 colon 5EE colon FF colon 238 colon 47B1. Yeah, that's still a little crazy. So we can further compress by expressing a single contiguous set of 0 blocks, right? So when we have a bunch of blocks of just 0, we can put a double colon. FE80 colon colon 5EE colon FF colon 238 colon 47B1. Still don't think that's too easy to say? I agree with you. Here's what I'm going to tell you about IPv6. It's not designed with you ever really needing to know what the addresses are, or to have to speak them, or to have to write them. There's a lot of automation built in. Only high-end IPv6 administrators need to worry about this. So don't freak out. Just wanted to give you a high-level overview. And with that, it does bring us to the end of this lesson. And as long as this lesson was, I will tell you that it was just the absolute tip of the iceberg when it comes to understanding IP addressing. So if you really want to get into networking, and I mean deep into networking, when you're done with A+, I really strongly recommend that you go watch Network Plus and learn all about IP addressing, where I have a series of lessons just on IP addressing, which are probably a grand total of 3 or 4 hours long. Okay, there's plenty more to know. But as far as this lesson goes, I thank you for watching, and I will see you in the next lesson.